Thank you for the kind invitation to present my work at this virtual Lumini conference. I have to say it's a slightly surreal experience, but I'll get used to it. So this is joint work I'm going to be speaking about with second-year PhD student Yudong Chen and my former PhD student postdoc Tengyao Wong, who is now a lecturer in statistics at University College London. Okay, so we all know that we're collecting vast amounts of data these days. An interesting feature of data that we collect is a lot of the time it comes in the form of a data stream, process that is evolving over time. So driverless cars are constantly picking up new data, wearable health devices similarly, and also astronomical sky telescopes, to just give examples. And when we're interested in data that's being collected over time, or can sometimes be things like location on a genome in genetics, it's very often the case that we're interested in change points in these. Of course, change points are a very classical area of statistics, dates back at least sort of 70 years or so. But the vast majority of this work has focused on what I'll call the offline problem. That's where you get to observe the entire data set, and then retrospectively you have to determine whether any change points have occurred and perhaps where they occurred. Online change point problem, where you're observing data sequentially and you want to try to declare a change as soon as possible after it's occurred, has also received quite a lot of attention in the one-dimensional case. It's under the banner of statistical process controlled. In fact, that area dates back almost as far, or perhaps at least as far, as the offline problem, and it's still an active area. But there's been comparatively little work done in the multivariate case of online change point detection. I should mention, though, several works that involve a scanning window, a moving scanning window, as one approach to tackling this problem, and I'll say more about that general. So the starting point for our work on the online problem was to come up with an appropriate definition of an online algorithm. And this turns out to be quite restrictive, but also quite important. So we'll say that an algorithm is online if the computational complexity for processing a new observation depends only on the number of bits needed to represent it. So there's just a couple of comments I should make about this. The first is that for our purposes, of course, we're only able to store real numbers as floating point numbers on computers. And so I'm not going to worry too much about the difference between a real number and a floating point number. In other words, when it comes to our theory, when we assume Gaussian observations and things, I'm not going to worry about the small truncation error in representing that as a floating point number on a computer. The important part of this definition is that the computational complexity is not allowed to depend on the number of previously observed data points. This turns out to be quite a strong restriction, and it's therefore quite difficult to come up with online algorithms that could have good statistical performance. Okay, so here's the problem setting that we're going to be considering. It's quite a simple data generating mechanism, but it'll allow us to, it'll provide a basis for theoretical study that I think is quite useful. So we're going to be considering the online change point detection for high dimensional independent random vectors. So there's going to be no time dependence between the observations in this talk. So the assumption is that for some unknown deterministic time z, which could be 0, but otherwise a positive integer, we have that the first z observations are generated according to a standard p-variate Gaussian distribution, and after the change point z, the observations change, and the change in distribution, but the change only happens in the mean vector. So the Gaussian distribution remains, the covariance matrix, the identity covariance matrix remains, but now we've got mean theta. So in many ways, this is the simplest sort of change that one could see. So one possibility is that theta is 0, and then of course you've got no change, and we'll say that the data are generated under the null. But if theta is non-zero, then we do have a change point, and we'll say that change occurs at time z, and we'll say the data are generated under the alternative. Another feature of the problem is that we're going to impose a known lower bound, and we'll call it beta, on the L2 norm of theta. And the notation for the L2 norm of theta is going to be this var theta. So there is a p-dimensional vector, but var theta is going to be a scalar quantity, the L2 norm of the vector theta. So the idea here is if we want to have a test with non-trivial power, then we're going to want to have some separation between the null and the alternative. Okay, let's try and get some more insight into sorts of restrictions that are imposed by being an online algorithm. Here is an example of an online algorithm. It's due to Page and dates back from 1954. And so he defined an online algorithm in the case where p equals 1, and I'm going to assume for simplicity that the change theta is positive. So what you'll notice is that if you look at the ith summand in the definition of the statistic Rn, this is the log likelihood ratio statistic for testing the null that we have a standard normal distribution against the alternative that our data come from a normal beta 1 distribution. So that's one observation, and this is the log likelihood ratio statistic for that one observation. And then what we're doing is we're looking at the cumulative log likelihood ratio statistic over the last H observations, and we're trying to maximize that. So we can look as far back as we like, and we can try to maximize it. So if we look at this picture here, we've got this cumulative log likelihood, this orange statistic, which is oscillating around here. And the Rn statistic is the difference between the current value of the cumulative log likelihood and the value it took at the global minimum up to this time. What you'll notice is that if you look at, again, this ith summand, then if you're before the change point, in other words, you're coming from a standard normal distribution, then we've got a negative drift in this term because the xi's got mean 0. So you're tending to come down here. But after the change, the mean is going to be beta in the correctly specified case where theta is equal to beta. And then you're going to be coming back up again So we can look at actually what Page's statistic is. It's his blue curve, and that's representing the difference between the cumulative log likelihood at the current time and the global minimum up to this time. And so this hits 0 at various times, and these times are renewal points of the process. So it's as if the process starts again whenever you hit 0. And what you can see about this statistic is it can be expressed as a maximum of where you were before and some function of the current observation, and then you just have to take the maximum of that with 0. So this latter expression is telling you that this can be computed rather efficiently in an online way, and we're going to declare a change if this statistic exceeds a threshold. That threshold only needs to depend upon this level. Okay. Another algorithm which seems superficially rather similar is to look at scanning windows. I mentioned previously that there's been quite a lot of work on scanning windows. So let's say we've got a scanning window with width W. Then the statistic we're going to look at is rather similar. We're going to look at the difference between the cumulative log likelihood at the current time and where it was W observations previously. So again, now we've got these dots, which are the log likelihood of each observation. We've got the orange curve, which is the cumulative log likelihood, and the blue curve is obtained by looking at the difference between the orange curve at the current time and where it was W observations ago, in this case 15 observations. And this also seems to be an online algorithm, but there's an important point to note here. And it is that as W decreases, your window size needs to increase in order to have power to detect this change. And actually what that then means is that the computational complexity of the algorithm depends upon beta, and therefore doesn't satisfy our definition of being an online algorithm. One more example that's been used in online change point detection is the Shirayef-Roberts procedure, and this procedure is even less of an online algorithm in the sense that I can't define it recursively. I need to be able to compute partial products from observations I to n for each I equals 1 up to n, and this is a sequential algorithm, but not an online algorithm. So the restriction of being an online algorithm is quite a strong restriction, but that's what to look for. So I'd better define what we would consider to be a good online algorithm. First of all, what we mean by an algorithm in this context, a sequential change point procedure, extended stopping time. So that's just a stopping time that can take the value infinity. It's with respect to the natural filtration. And then there are two criteria by which we could judge it, the patience and the response delay. So what we call the patience, what's often called the average run length to the false alarm, is just the expectation of n under the null hypothesis. That's like our type 1 error, and so we'd like to control that at least some nominal level. When it comes to response delays, there are actually two different versions, or this is similar to a power in a regular hypothesis testing problem, type 2 error. So there are going to be two different sorts of response delay. There's an average case response delay. So this is where we look at the worst case of where we could put the change, but we take the average and then of difference. This is the n minus z is the delay here, but I don't want to get a bonus for declaring a change before it's actually occurred, so I'm going to take the maximum with 0. In addition to the average case response delay, we also have a worst case response delay, and that's where instead of taking the average over the pre-change observations, I'm going to take the essential supremum over the pre-change observations. So what's pretty clear from these two definitions is that the average case response delay is going to be no larger than the worst case. Both are interesting quantities to us. Okay, and here is I'm now going to describe the multiscale online change point detection algorithm that we introduced. It's called OCD, which stands for online change point detection. So our algorithm is going to be made up of different components. In particular, it's going to be made up of both diagonal statistics and off-diagonal statistics. So the diagonal statistics simply look at each coordinate individually. And we're going to denote coordinates with superscripts so that our ith observation vector has p components, and these are denoted with superscripts here. So at each time n, and for a particular choice of scale b, which I'll have to tell you about later on, and then for every coordinate j, we compute Page's statistic for the jth coordinate. So this is we talked about earlier, and it's Page's statistic for testing a null that the observations come from normal 0, 1 against an alternative that it comes from normal b1. But in addition to the vertical height, which is Page's statistic, we're also going to record what we call residual tail lengths. These are the TNBJs, and that's just the time since we hit the last minimum, since we hit the 0 last. So these are what we're going to call the diagonal statistics. And they're going to be good, effective statistics for us in a very sparse case. In particular, if there were a change in theta only in one coordinate, then we would hope that in that coordinate, this statistic ought to be powerful for detecting that change. But we'd also like to be able to detect more complicated changes where changes happen simultaneously in several coordinates simultaneously. In other words, we like to be able to borrow strength across the different coordinates. And to do that, we're going to look at some off-diagonal statistics. So what we'd somehow like to do there is to aggregate over the data in several coordinates, but we'd like to do so after the change has occurred. Of course, the trouble is that we don't know when the change has occurred, and different coordinates are giving us different evidences for when that change occurred, and the evidence is coming in the form of this residual tail length in that coordinate. So the idea is to look at all possible tail lengths we could have amongst the different coordinates and think about aggregating the residual sums over that tail length, but across all the coordinates. So this picture probably explains things rather better. So we fix the jth coordinate, and that gives us our residual tail length. And then in the j prime coordinate, j prime is 1 in this case, we're going to be adding up the observations that we see from over the last TNBJ observations, and that gives us the j prime comma jth entry of a matrix A. So that's what we do when j prime is 1, and then in the second coordinate we're also, so in other words, to compute the second entry of the first column of this matrix, I just come down here and I aggregate the observations over the second coordinate, but over the same length. And I go through the coordinates in turn, and that completes this column. And then I move on to a different j, and that gives me a different residual tail length, but I perform the same kind of aggregation in this matrix. And then we'd somehow like to be able to aggregate the information that we get in this matrix A. And we do this by forming an off-diagonal statistic that's anchored at coordinate j, and we're going to do that for each possible choice of j. So if you look at how this off-diagonal statistic is formed, we're adding up the squares of the entries of this A matrix, and there's some possible thresholding here, but since we can set A to be 0, and we will set A to be 0 in some cases, let's first of all ignore this thresholding and think about this quantity here. So under the null hypothesis, it turns out that this quantity is going to have a chi-squared-1 distribution, and what's crucial is that since we're summing up over coordinates that are different from j, this is going to be, we're going to have some independence, which means that under the null hypothesis, this will have a chi-squared p-1 distribution. But under the alternative hypothesis, this is going to have a non-central chi-squared distribution, and that's going to be the basis for how we can hope to detect a change. The reason for including this thresholding function here is that if we know somehow that the change is sparse, then we don't want to be aggregating over all coordinates because there's too much noise accumulation. And that's why we threshold here, and we try only to aggregate over the large coordinates. Okay, so you remember that there's a choice of scale involved in our statistics. That's the B parameter. And I need to tell you how to what range that's going to range over. And it's going to range over this sort of signed dyadic grid. For slightly technical reasons, it's convenient to define both a grid B and then to add 2 more elements to this, which is just 1 more term. It's like taking L to be 1 larger than what we had here to augment that to B union B0. So for our diagonal statistics, we just take the maximum over all coordinates over all scales in the augmented dyadic grid of Page's statistic. But for the off-diagonal statistics, we also take the maximum over all coordinates, but for the scales, we just do it over this slightly smaller grid, the B here. And the idea is that we're going to be able to declare a change when either of these statistics is large. So here's the pseudocode for the algorithm in the end. We observe data sequentially. We have a known lower bound on the L2 norm of the mean change. We can choose a thresholding level A, if we, which may be 0, that would correspond to no thresholding. And then we've got 2 declaration thresholds. So these are the levels that our statistics need to exceed if we're to declare a change. And so I won't go through this line by line. It's just describing a little bit more formally the algorithm that I've just outlined. But an important point to note is that the computational complexity of each iteration is of order p squared times the log of EP. So in other words, it does satisfy the condition of being an online algorithm according to. Okay, so I said that we've got a choice of A to make, and I'm actually going to consider 2 possible different values. In the dense case, we don't need to do any kind of thresholding, and we're just going to set the A to be 0. So that gives me a particular version S of D for dense of our off-diagonal statistic. But for the sparse change, I'm going to need to choose a positive value of A to try to reduce the variance of the statistic. And that gives me a sparse version of the off, and I'll write that as S off with an S for sparse. So in total then, we've got 3 statistics to track, and we're going to declare a change whenever the first one of these exceeds its respective threshold. I haven't told you yet how I'm going to choose the thresholds. Okay, of course I'm going to choose the thresholds in order to be able to control the patients, at least at some nominal level. But the basic idea is that the diagonal statistics are going to be useful or powerful for detecting changes when the signal is concentrated in one or only a few coordinates. That's when the sparsity level is very low, and change is not so sparse, then the off-diagonal statistics are going to be more useful for borrowing strength across the different coordinates to detect change. Okay, actually it turns out that for our theory, it's convenient to work with a very slight variant of this OCD algorithm. This is something that we've actually found not to be so necessary to implement in practice, but I'll try and explain why it's convenient for our theoretical analysis. So remember that what we'd like to be in this favorable situation where the residual tail length doesn't extend beyond the true change point, because what this means is that we're going to only be aggregating over post-change observations in computing our off-diagonal statistic. That would be the favorable situation, but of course we can't guarantee that we're not in this situation where the residual tail length is large enough that it means we're aggregating over pre-change observations as well. And that's going to be pretty difficult for us to control, particularly in the for the worst case response delay, where we need to take an essential supremum over all pre-change sequences. And the issue here is that as we observe each new observation, we either increment this statistic by 1 or we set it back to 0. But if we keep incrementing it by 1, then we're not guaranteed that we're only going to be aggregating over post-change observations. And the idea then to how to get around this problem is to actually only look to aggregate over about half, or say 3/4 of the length of TNBJ. And what that means is that instead of increasing by 1 each time, we're only increasing by something less than 1, and so eventually we will be only aggregating over post-change observation. This then, and that would look something like that. The question then is, how can we ensure that we're only aggregating over, let's say, roughly half or 3/4 of these data points, but do it in an online manner? Or slightly more formally, if you just, and let's reduce it to a one-dimensional problem, if I give you a sequence of real observations, how can you keep track of just the last half or 3/4 of the observations at time t in an online way? And so here's the idea here. We've got time that's going along here, and the tour is going to tell me how many observations we're aggregating over, and I'm going to look to control that to be something between a half and 3/4 of the current time. And it's going to be this lambda sequence which is going to be aggregating the relevant observations. And the way it's constructed is aided by an auxiliary sequence which I'll call lambda tilde. But for the lambda sequence, the idea is that at a if your current time point is not a power of 2, so let's say time is 6, then we just add the new data point to what we had previously forward. But if we hit a power of 2, what we're going to do is replace the current, we're going to add in the previous value of the lambda tilde as well as the new observation. So when we get to time 4, we replace what we had previously with the corresponding entry from lambda tilde, and we add the new observation x4. When we get to x8, we had x5 plus x6 plus x7, which we replace what was there before, and we add the new observation x8. So in this way, the lambda is always tracking at least half of the most recent observations. In fact, between half and 3/4 of the most recent observation. Okay, and then so what that allows us to do is to slightly modify the algorithm. It's a little bit complicated to follow in real time, but it's not that difficult to code. And this allows us to prove theoretical guarantees for the OCD prime algorithm. In practice, as I said, it doesn't make very much difference compared with the original OCD algorithm. Okay, so let's talk about some theoretical guarantees. To obtain theoretical guarantees, I need to tell you how to choose the threshold levels. And here are going to be our definitions of the threshold levels. It involves this function psi, which is a relatively straightforward function. Many of you will recognize this from tail bounds of chi-square variables. Okay, and the nice feature of making the choices in this way is that under the null hypothesis, the adaptive version of OCD prime, that is the one that declares a change when the minimum of 3 statistics exceeds its threshold level, satisfies the patient's guarantee that we desired, controlling the patients at least at level gamma. In order to talk about the response delay, I need to introduce a notion of effective sparsity. So this is the smallest s, taking values in this dyadic grid, such that the cardinality of the set of coordinates for which the change vector is at least sort of non-trivial proportion of the overall L2 norm of the change is at least the s of theta. So this is pretty similar to usual notion of sparsity. It's just telling us which coordinates are making a significant, have got a significant change. So here's our main theorem on the response delay of the OCD prime algorithm. So we're working under the alternative hypothesis now, where a change happens at time z, and that our post-change signal satisfies that the constraint that its L2 norm is at least the beta that we know in our algorithm. And then we're going to provide response delays in both the worst case and the average case. The worst case response delay, well, let's not worry too much about logarithmic factors here. It's essentially s over beta squared, okay? So you can take advantage of effective sparsity in this. But actually, there's a slightly different expression in the average case, you've got the same expression appearing here as we had before, but it's actually the minimum of this with another quantity here. So let's look at what's going on here. And it's easiest to initially think about this in the case where the beta, the lower bound on var theta, is actually equal to, or at least of the same order as var theta squared. Because in that case, I know that the square root of s is going to be smaller than, no, larger than the square root of p, so the maximum is going to be attained in this term here. So ignoring logarithmic factors, and in the case where var theta is of the same order as beta, then I'm going to get an average case response delay of the minimum of s and the square root of p divided by var theta squared. So put slightly differently, or just pictorially, at least in this case where var theta is the same order of beta, and we've got this relatively mild condition on the relationship between gamma, beta, and p, then we have these two bounds on the worst case and average case response delays of our procedure. So in both cases here, the blue lines are representing our adaptive algorithm, which is the main one I introduced. But there are also sparse and dense versions of the algorithm that look for changes of specific types. And what you can see is that the dense version of the algorithm is unable to take advantage of the sparsity here. It's just can't exploit it, at least when the sparsity is smaller than square root of p. It does pay a price in terms of worst case after that. And the sparse algorithm performs poorly in the average case when the sparsity exceeds the square root of p. But fortunately, the adaptive algorithm is able to get the best of both worlds in these cases. So there's an interesting elbow effect for sparsity at level square root of p, and that type of elbow effect has been observed previously in other high-dimensional point problems. So here's an animation to illustrate the OCD algorithm. And so what we have here, we're tracking the three test statistics, but we're normalizing them by their thresholds. And what that means is that we're going to be declaring a change as soon as the first one of these statistics exceeds the level 1. And in this simulation, the change point actually is going to occur at time 900, and we're in 100 dimensions, and we've correctly specified the beta is equal to the magnitude of the signal change. So on the left, we've got a rather sparse situation where the change is only occurring in 3 coordinates, and on the right, it's completely dense, and the change is happening in all of the coordinates. So you remember that for the sparse settings, the diagonal statistics and the sparse version of the off-diagonal statistics are specifically designed for this situation, and you can see that they're the first ones to declare the change in this case. On the other hand, for the dense case, that's where the blue curve, the S of D divided by T of D should be performing well, and we get up to time 900, we see that it's the blue curve that's first to exceed the level 1 and will therefore declare a change. So in this case, you can see that the response delay is about 30 in the sparse case, and if we run it once more, I think it's about 100 in the dense case. And that's quite interesting because P is 100, so the square root of that is 10, and so what we're seeing is that it's taking about 3 times as long to declare a change in this sparse case, in the dense case, as it does in the sparse case, and that really is exactly in line with our theory on the previous slide. So now I want to compare our OCD algorithm with some other alternative approaches. As I mentioned, there are only a few that have been proposed. One is the May algorithm, which involves an L1 and an L infinity aggregation of likelihood ratio tests in each coordinate. The second comparator is an algorithm by Xi and Sigmund, which uses a scanning window based approach that we discussed earlier, and tests the null hypothesis that you've got no change against a normal mixture alternative where each coordinate has a change with probability p0. The Chan algorithm is rather similar to the Xi and Sigmund algorithm, but it uses different values of the tuning parameters. So we're going to work in 100 dimensions and 2000 dimensions in a quite sparse, not very sparse, and not at all sparse setting, and with different values of var theta. So theta is 1, corresponds to correct specification, three different signal to noise ratios, I should say. var theta is 1, 0.5, and 0.25. And here we're going to generate our alternative as var theta times u, where u is uniformly distributed on the union of all S-sparse unit spheres in R to the p. In other words, you just choose your S coordinates where you're going to have a change uniformly at random. Okay, a practical issue is that the choices of thresholds that I mentioned before that give us our theoretical guarantees turn out to be a little bit conservative in practice. There are bounds involved, but what you can do is to compute them using Monte Carlo simulation, because we just need to generate data under the null and see how long it takes for these statistics to exceed various thresholds. Now, of course, the choices of these thresholds are coupled together, so there's a slightly delicate choice of how you do that. I won't go into it in too much detail here. You can look at the paper for more details. But there's a relatively principled way in which we can couple together these choices. Okay, and here are the results we see in terms of the estimated response delay. This is over 200 repetitions and with a nominal patience level of 5,000. So the OCD algorithm does pretty well in simulations. Really across all settings. There are a few settings where it's slightly beaten, but not by too much, by the Chan algorithm. But other settings where the Chan algorithm performs rather poorly. So the point here is that, as I mentioned previously, if the signal strength is large enough that the scanning window width doesn't need to be increased, then that's going to do very well for detecting changes. So the Chan algorithm is going to do well in the strong high signal to noise ratio settings. But in lower signal to noise ratio settings, the window width isn't large enough to include enough observations to detect the change, and that's why you see the large response delays. Okay, let me wrap up then. The aim of our work here was to introduce a new multiscale method for high-dimensional online change point detection. The basic idea is to perform likelihood ratio tests against simple alternatives of different scales in each coordinate, and then to aggregate these statistics in different ways so as to be able to detect alternatives of different types. So the R package for our algorithm is called OCD, and it's available on CRAN. And then the main reference is this one here, and the paper's available on the archive. Here are some other references, and I thank you very much for your attention.